here for this session. So everything that I go through here today will be recorded and then posted, hopefully on the YouTube channel if everything works according to plan. Again, I apologize for the lateness. My electronics 2 lecture last week was so good that they had to put me in jail for it. So on the way here, I ran into the cops. So that's why I'm a little bit late, but hopefully this lecture is going to be as good. And we're going to get through a lot of things today. So this is the practice final that Professor Gad posted on his Brightspace when I took the course. So this is the one I'm going to be going through. I'm going to be solving questions very slowly, going through every single step and every detail. If you want to, you can copy down the notes. You can follow along. You can ask questions whenever you feel like it. One thing I will say that because this is going to be posted on your YouTube, I might not post the notes. All right, everything that I go to, I might not post them. So if you have questions, you can ask in between. But depending on how many people actually want the notes at the end of the session, I will see if I can provide you the notes. Okay. So with all that being said, do we have any questions before we start? Yeah, what's up?
Est-ce qu'on pourra avoir le document? Comme ça, on peut le faire en même temps.
Le document?
Ouais.
C'est celui qu'il a. Oh, okay. It's on the Brightspace. Yeah, it's provided to you guys, right? Yeah. So I mean, you can take that. I know it's going to take me a little bit of time to send it to you right now. Okay.
Sounds good.
All right. What was I going to say? I was going to say one more thing. Okay, here is another document that I prepared. It's basically the whole class combined in 5 pages. All the need to knows to be able to pass the exam and do very well is all combined in this document. So if you guys are interested in having that as well, come talk to me at the end of the session. Okay. All right. Yeah. If you.
Coffee, hot chocolate or mocha coffee? Black coffee. Yeah. Coffee. Black.
All right, we're gonna get started here. So, since you guys can all see my screen on the Teams, and as well, you can hear me clearly. We're gonna get started. So this is the first question we're gonna solve today. Before I start, I need to make an ad. I have this calculator right here that I want everyone to get today. It's the TI-36 Pro. It solves 3x3 matrices. It's not programmable, and you guys can use it in any exam you want. And especially if you're in electrical engineering, you're going to have to solve a lot of circuits, well, throughout your degree, right? So having this calculator is going to help you out a lot doing all matrix calculations. That sound good? Okay, we're going to get started here. So it says using mesh current method, determine the value of currents I1, I2, and I3. So I got the circuit right here, and I'm trying to determine what these currents are. So that means I'm going to have to do how many KVLs in total here if we're looking at the circuit from a bird's eye view. How many KVLs am I going to have to do? 4? You sure? You're close. If you just have to gauge, probably just 3 because you have 3 currents. The reason you would have to do 4, which I get why you're saying, is if you have a current source in between 2 meshes, right? Then you would have to do a super mesh. But since you got only 3 currents here, you're only going to have to do 3 KVLs. Now, because this current is going clockwise direction, that means it's going to go through the positive end of the resistor. Every time a current passes through a resistor, it's a voltage drop. So it goes from positive to negative. Same thing here, positive, negative, and then positive, negative. So now what I'll do is I'll write here KVL at I1. The first equation we're going to have is going to be 10 times I1 minus 3 times VA plus 20 IB equals 0. So that's the first equation I got here. We got 20 IB, we got 10 I1, and then we got minus 3 VA. Now, when I look at this equation, where does the 10 I1 comes from? Where does that come from? The 10 I1.
From the first resistor.
Exactly, from the first resistor, right? You multiply, KVL is basically the sum of voltages, right? So if you take a current, you multiply it by a resistor, you're going to get a voltage. So here you're going to have 10 times I1, that's where it comes from, okay? Minus 3 VA, this is a dependent voltage source. It depends on the voltage source VA, which is right here. Why minus? Because when I go through my current here, when I follow it, I find my minus sign. Does that sound good? So that's why it's minus 3 VA plus 20 IB again. This is a voltage source, so that's why I'm going to add 20 IB to it. So that's the first equation. Now I'll write my second equation, KVL at I2. This equation is going to be, again, can I get some volunteers to just write this equation out for me? So then it's more interactive for everyone here.
So
yeah,
20 I2.
20 I2, right?
Minus 20 IB.
Minus 20 IB.
Then you got VA.
Plus VA equals what?
0.
equals 0. All right. So that's my second equation. Now I'll write my third equation, KVL at I3. All right. Now, someone else, any volunteers to write this equation down for me? For I3. Where can we start by? I always like starting from the ground up, right? So if I'm starting from the ground up here, what's going to be the first term of my equation?
Minus VA.
Minus VA, right? Because I'm seeing the minus times VA. Or one more thing I can write is plus 5 times I3, right?
Right.
That's one more thing I can write because 5 times I3 is going to be equal to minus VA, Ohm's law.
Then wouldn't it be better for the KVL at I2 to replace it by minus 5 I3? Minus 5 I2?
Minus 5 I2?
Yeah.
Yeah. Actually, it's going to be like, but it's not only one current, right? It's going to be 5 plus 5 I3 minus I2, right? You got two currents flowing through here, right?
Right.
If you look at, you got I3 here and then I2 here.
Right.
So that's why I keep it in voltages first. And then I write VA in terms of the currents that I know. And when I plug it back in, there are no numerical mistakes, right?
Makes sense.
Because if you do a numerical mistakes in writing your equations, when the prof is going to correct it, he's going to consider that to be conceptual. So the main thing I would say as a word of advice is when you're writing your KVLs or any equations you're going to solve, make sure those equations are correct. Because then if you do the math, going through the algebra, there's mistakes there. It's okay. It's mathematical. But if your equations are wrong to begin with, you might get half the points of that question. So if the question's out of 10, you're only going to get half because your equations are already wrong. But if you write the correct equations, that's probably 8 out of 10 already. Okay. So KVL at I3, I got here. If I follow my KVL here, right? I follow the KVL. It's positive 5 I3 minus I2. But I'm not going to do that yet. I'm going to follow this voltage instead, right? It's going to be minus VA plus 3 VA. And if I follow it, keep on going, plus 10 volts. So I'll do that nice and slow. We got minus VA, which is here. And then we got plus 3 VA. Okay. Plus 10 equals 0. So this is going to be my third equation. So now I have 3 equations. I'm supposed to be having 3 unknowns. If I have 3 equations, 3 unknowns, I have 3 KVLs. What are my unknowns supposed to be? I got 3 of them. What are my unknowns supposed to be in my equations for it to work?
I1 and 2 and 2.
Exactly, right? I cannot have any VAs. I cannot have any IBs. So anything that's annoying in this equation, I need to write it in terms of my mesh currents, right? That's why it's the mesh current method. You want to take your circuit, you define it into the 3 currents that's going to allow you to find anything you want in that circuit. So over here, if I look at my first equation, I have VA and I have IB, which is kind of annoying. So let's deal with VA first. VA right here is this voltage across this resistor, right? How can I describe VA in terms of mesh currents? Any idea?
So 5 times I3 minus I2.
Exactly. If I look over here, I got one current going here, which is I3. If I follow this mesh, that's going to be I3. And then the second current flowing in here is going to be I2, which is I2 right here. Okay. Now, VA is a voltage going down like this, right? Right? It's going to be like this. So I need to pick the current that goes in the direction of VA first. So which current is going in the direction of VA, which is plus to minus? Is it I3 or is it I2? Right? Because I'm going from up to down, right? If I look at this sign right here, current always flows from positive potential to negative potential, from high to low. If I look over here, I got one current going from high to low and another current going from low to high. If this is my positive end, which current should I write first?
I2.
I2. So it's going to be VA. I'll write it right here. VA equals 5 times I2 minus I3. Why I2 minus I3? Because I2 is the one following the path of the voltage, that voltage difference. Now I can see that I have VA in terms of mesh currents, which is I2 and then I3. Now, if we're looking at IB, what is IB equal to?
Minus I2.
Why would you say that?
Because we see that the IB is going to the opposite direction than I2.
Exactly. So IB here equals minus I2. Now, I need to take this and replace it into my equations. So I'll just call these equations A, equation B, equation C. So equation A would become 10 times I1 minus 3. VA is this thing right here. So I'll take that and substitute in there. Times 5 I2 minus I3 plus 20 IB is just minus I2. We just wrote it here. Minus I2, and this is equal to 0. So now I'm just going to clean this equation up. I have 10 I1 minus 15 I2 minus I3 minus 20 I2 equals 0. So 10 I1 minus 15 I2 plus 15 I3 minus 20 I2 equal 0. 10 I1 minus 35 I2 plus 15 I3 equals 0. Any question on how I got this first equation here? I just ran down through the math. All right, there's nothing fancy here. I just had this equation to begin with. All I did is I took VA, replaced it in here, right? And then I took IB, I replaced it in here. I expanded in terms of I1, I2, I3, and I got this equation right here nice and cleaned up. So I'm just gonna box that equation in orange because it's gonna come in clutch later. Yes. What's up? Right.
Then we have two super
We have two super mesh. Okay. Super mesh.
Textbooks that can have both independent or independent.
Right. You can have both actually.
Both.
You can have both. You can have any dependent or independent and still use super mesh and get the right answer. So you're saying here, if I had a current source like that, for example,
Yeah.
right? The only thing you would have to do is something like this. Yeah. Because the reason you have to do this, because if you do a single KVL, if you have a current source here, you don't know the voltage across it because it's a current source. So to be able to escape that problem, you do a bigger super mesh, right? And then you don't have to worry about this at all. And now if here you had another current source, your super mesh would be of that nature.
We can write KVL.
It's not going to be harder. You just have to make sure that, say for instance, you had a current source here, right? Your KVL is going to be 20 times I2, but as you go through here, when you're following that super mesh, it's going to be 10 times I1 instead, right? You just have to make sure you're keeping the currents in track for that super mesh. I think maybe throughout this, they're going to come opportunities where we have to do super meshes here, but if there are none in this final, and if you guys want to still see me do a super mesh example, I can go through that later as well. Dependent voltage source and dependent. If it's a dependent voltage source, you don't have to do a super mesh because it's still a voltage.
Yeah, one of them is that, for example.
I can go through that after the practice final. All right. Okay, so we have this first equation. Now just look at my second equation right here. So this is equation B. I'll write it down here. We have 20 I2 minus 20 IB plus VA equals 0. Any idea on what to do with IB and VA here? What can I do?
I'll just replace them with the
With the known values. Okay. So 20 I2 minus 20 IB is minus I2. I wrote it right here in the box. Minus I2 plus VA is 5 I2 minus I1. 5 I2 minus I3, sorry, equals 0. Now I'll just expand further. 20 I2 minus plus 20 I2 plus 5 I2 minus 5 I3 equals 0. So 20 plus 20, that's 40, plus 5, that's 45 I2 minus 5 I3 equals 0. But now, if we notice in this equation, I don't have an I1, right? Now, for reasons that's gonna come clear later, I'm just gonna write 0 times I1 plus 45 I2 minus 5 I3, and that is equal to 0. And I'll box down in orange. That's my second equation in terms of I1, I2, and I3. Yeah, I saw that. My bad. I1 here. Okay, so that's my first equation. That's my second equation. Time to find the third one, which is right here. Now, I can clean this up a little bit because minus VA plus 3VA, that's just 2VA, plus 10 equals 0. So now, equation C right here, I got 2VA plus 10 equals 0. VA, again, I can substitute it because I have it in terms of mesh currents. So 2 times 5 I2 minus I3 plus 10 equals 0. All right, 2 times 5 is 10. I2 minus I3 plus 10 equals 0. So I have 10 I2 minus 10 I3 equal minus 10. Again, we don't have an I1 in this equation, but for the reasons that gonna come clear a little bit later, it's just gonna be 0 I1 plus 10 I2 minus 10 I3 equal minus 10, and this is my third equation. Now, if we look at these three equations, what can we notice about them? There are a couple things we can notice.
So we have three equations with three unknown values.
Exactly.
So we can just calculate directly.
That's one thing. You got three equations with three unknown values, and you can calculate them directly. What's the second thing we can say about the unknowns in your equations? The unknowns, are they the unknowns that you want? Yeah, it's I1, I2, I3 because they're the unknowns that you want. So basically, we're set up for success here. I have three equations containing the mesh currents I1, I2, I3. Basically, the question has been answered. The things that left is basically to just combine everything and then get the actual values for I1, I2, I3. Here, if you run into computational mistakes, that's when you'll probably lose like 1 or 2 marks. But if these three equations that are in orange right now are wrong to begin with, that's when you might lose actually half the mark for that question. Now, this is where this calculator comes in clutch because I have three equations and three unknowns, right? So what I can do is I can write this in matrix form. Let me just copy paste all of these things right here so I show you how I do that. Copy, paste, right? Paste. Then, all right, there we go. So now I have three equations and then three unknowns all on top of each other. I have to make sure that my equations are in the form of I1, I2, I3, I1, I2, I3. If I meet this, then I can basically have a matrix of that nature right here, where these are going to be the right-hand side of my equations, and these are going to be the coefficients of my unknowns. In the first equation, I have 10, minus 35, and then 15. Second equation, I got 0, 45, minus 5. Third equation, I got 0, 10, and minus 10. And then on the right-hand side, I got 0, 0, minus 10. Do you understand how we got this?
Yeah.
How we went from the equations to the matrix. Now that I have this matrix, all I need to do is to plug it in here, and it's going to give me the answers. That's the life hack for this course. If you have this calculated, mesh current, three unknowns, three equations, write it in that form, put it in here, no mistakes, 100%. All right, that's 10 marks already done. So I just got the answers right here. The answers are basically here. If I put in the calculator, we got the answers here. But if you went ahead and actually did this Gauss-Jordan elimination by yourself, probably going to make a mistake. That's one. And second, you're probably not going to get the right answer, and it will take you a long time to do that. So that's how I got these numbers right here by doing this analysis. Do we have any questions at any point that's not clear that I can go over again or anything like that? No questions? All right. This is the second example. I'm just going to erase that because I want to go through it again, like step by step. Okay. So we got this circuit in steady state before the switch closes at t equal 0. The input to the circuit is 24 volts. And then the output right here across the 3 ohm resistor is given by this equation as a function of time when t is much, much bigger than 0. So we have this kind of situation. What is it asking for? It's asking us to determine the value of the current IT when time is bigger than 0. Okay. Now, there are a couple of things to keep in mind when we're dealing with a circuit in steady state or a circuit that's time dependent. The first thing to keep in mind when solving a question like that is to know what time interval you're working with. Are you working with bigger than 0? Are you working with exactly at 0 or less than 0 or t at infinity? Because these are different things. When it's less than 0, your switch status is different. When it's greater than 0, a switch might change, you know, something like that to be able to, you need to be able to know what you're working with, basically. So question A here is telling us to find IT for t bigger than 0. Okay, I of t. I need to go in the circuit and spot where that is. So I'm going to go right here, and then I find out that my I of t is here. And if I backtrack my I of t, I see that the flow of I of t is coming from here, right? This is the flow of I of t. It's flowing through all of these resistors right here until here. That's where I of t is flowing. So that means I of t is flowing through the 3 ohm as well, right? So what can I use to be able to find the current in this case?
The VO of t.
The V of t, right? The V of t. I can basically use Ohm's law. V equals IR. I have the current here. I know the resistance. No, I don't have the current. I know the current passes here. I have the voltage and I have the resistance. I have voltage, resistance. I can find current. So using Ohm's law, I know that V equals IR. So I'm going to have V output equals I of t times the resistance. Now, I want the I of t, so I'll just do I of t equals V output divided by the resistance. Now, what's the value of V out? It's given, right? It's given. It's right here for t bigger than 0. So I've just taken a substitute. So we have 6 minus 3 e to the minus 0.35 t divided by r, which is 3. That simplifies to, if I split the denominators, is 6 over 3 minus 3 over 3 e to the minus 0.35 t. This is 2. This is 1. So I of t equal 2 minus e to the minus 0.35 t amperes. And I need to make sure to specify that t is much bigger than 0. So then when the prof is reading these answers, he's going to understand that, hey, this person knows that this answer is only valid for t bigger than 0 and not infinity or before. As soon as I specify my answer and in the correct time range, you can box it up and they say this is your final answer. Any questions on how we found I of t and why we chose V output, the equation, and why we did Ohm's law? Any questions on why we did Ohm's law and why we chose the output and then how we found this current? Questions about that? No questions. Okay, we'll move on to the next part here. It's saying deduce the value of I0 plus, the value of the current just after the switch closed. Okay, so now we have the circuit that's given up right here. It's saying find the current value at I0 plus. What does that mean? I0 plus.
So just after the switch closed.
Exactly. So slightly above 0,
Yeah.
but very close to 0 still. Okay, so we want to find I0 plus. Now, what did we learn in class? In class, it's basically, I think Prof. Gad went through this. I0 plus, because it's so close to 0, it's equal to I0 minus. So to be able to find I0 plus, I need to find I0 minus. And if I want to find I0 minus, I'm working with t less than 0, right? So we're working in the t equals 0 minus or t less than 0. What happens at t less than 0? There are a couple of changes that happens to the circuit. Very fundamental changes, very, very important changes that happens when working at t less than 0. Exactly. The inductor is going to act as a short circuit. And then one more thing, this switch closes at t equals 0. So before t equals 0, it's still open. So my overall circuit is going to turn into something of that nature. You're going to have your voltage source here, 24 volts. 24 volts. This is R1. This is R2. R1, R2. This is 3. And then this is ground. And then here I put 2 dots. Why do I put 2 dots? It's just to indicate that this is a short circuit replacing that inductor. Okay, this is the short circuit replacing that inductor. And I have a habit of doing this as well. This is just to indicate that the switch was there, but it's open. Obviously, it does not electrically change the circuit because there's no current flowing through that open circuit to begin with. There's no current here. But for me to, it's just a method for me to tell the prof that, hey, I know what happened here. I know that that switch is supposed to be open and that inductor is a short circuit. Now that I have that down, I can easily find the value of I0 minus. So over here, I know that I0 minus is going to flow through here. How do I know I0 minus is there? It's basically the same thing at I of t, same place, except at a different time interval. Now, if I look at this circuit, what can I say about the resistors? What kind of combination are they in? And if they're in series, that means I can combine them R1 plus R2 plus 3. I don't have values for R1 and R2, So my answer for I0 minus is just going to be composed of these unknown values as well. Exactly. You can do that too. You can do that too. Right? But I already did those. I already did those questions at home. That's why I'm going through it like this. Here, you want to find R1 and R2. So it kind of makes sense to already do it in a step ahead so that when we reach here, we're kind of a little bit ahead of the game here. Okay. But exactly, if you want to find the value of I0 plus, you can take that and plug in the equation of time and you have the right answer for sure. So here I'm just going to write my equation for I0 minus. These resistance are going to be in series. So my Ohm's law here is going to be 24 equals R1 plus R2 plus 3 times I0 minus. This is just our equivalent, the series combination. Okay. So I0 minus is 24 over these sums. Let me box that. Okay. Now we have a value for I0 minus. Again, if you have your value in terms of unknowns here, it's a correct answer. If you plug it in there, it's a correct answer as well. So two answers are permissible. What you just said right here is basically use this equation and plug in 0 here, right? So you're just gonna get 2 as your answer. 2, yeah, 2 minus 1, my bad. 2 minus 1, which is 1. Any questions on this part right here? How we found I0 minus? No questions? Okay. Now we want to find the resistances of R1 and R2. Now, the first thing that I want you guys to realize here is we have this circuit going on here, okay? We got 2 resistances. How many unknowns is that? 2 unknowns. So that means I'm probably going to have to deal with how many equations to be able to solve this. I got to find 2 equations. The first equation is pretty simple. I'll just do it in the blank space right here. I have I of t equal 2 minus t to the minus 0.35 times t. So if I want I0 plus, I just plug in 0 plus in here. E to the 0 is 1. So this is 1. Now, this value here is the same as this value here because I0 minus is equal to I0 plus. What does that mean? It means that this has to be equal to this. So that means I'm just going to do this here. 24 over R1 plus R2, this is R2, plus 3 equal 1. So I have 24 equal R1 plus R2 plus 3. So R1 plus R2 should be equal to 21. This is the first equation that I have that contains 2 unknowns. And then that means I cannot solve it yet. That means I need a second equation that's going to give me another equation in terms of 2 unknowns, so I can do systems of equations to be able to solve that one. How can I find a second equation? I0 plus, but that's the same as I0 minus. Can you do that for the circuit?
Yeah, can you draw the circuit for t greater than 0? It'll be a different circuit. You'll have a different KVL, and then you'll be able to solve.
That's a good point. But the thing is, when you want to find I get what you're saying. If you do for t greater than 0, your voltages or currents are going to be functions of time, right? Okay, so if you have a function of time divided by a function of time, your answer will be a function of time. Okay, so that means, can you have a resistor as a function of time? Is that possible? Is it possible to have a resistor that kind of changes with time because of your circuit? The resistor is a constant value, right? So that means what you're saying is a correct approach, but not quite there. But you're close. If you take time and you bring it as far as possible, right? As t reaches completely to infinity, your circuit is going to stabilize. Okay, so when your circuit stabilizes at t equal infinity, that means all of your components again are acting like short circuits and open circuits, and it's basically a DC circuit at this point, right? It's basically a DC circuit, and you can compute your values again. So what I'll do here, I'll draw this circuit as t equal infinity, and then do the same type of analysis I just did. Now, there's only one change that's going to happen when t is at infinity. If we look at the circuit, right? There's one change that's going to happen. The switch, what happens to the switch at t equal infinity? It's going to be closed. So if I look at the circuit here, one sec. What happens to the inductor at infinity? It's shorted again, right? It's shorted again. This is shorted. and then this is shorted. So in a rush during the exam, you might just say that, hey, at infinity, I know that my inductor is short circuit, so all I can do is just use these same values again. Not entirely true. Why?
Because R1 is going to be in parallel with just
Exactly. Yes, the switch is closed. So now if I'm gonna do t equal infinity here, I need to modify this circuit. Paste. This switch is closed, and then this is gonna be I at infinity. Okay, now we have this circuit. What happens to R1?
just disappear.
It disappears. Okay. Okay, just it disappears here. Okay, now I can use the same approach, right? I at infinity equals 24 over R2 plus 3. Any questions on how I got this? This is just Ohm's law again, right? I have two resistances in series. I add them up. Voltage over current. Voltage over the resistance is going to give me the current. Okay, that's how I found this. Now I have an equation that's composed of one unknown. That means I need another equation to be able to equate this to something. So I know this equation already here. Here, I can plug it in infinity, but I'm just going to rewrite this as 1 over 0.35 t. These two equations are the same thing. Negative exponent is 1 over exponent to the positive. Now, I at infinity will be 2 minus 1 over 0.35 times infinity. This is basically a very, very large value. And when you divide by a large value, what happens to the overall answer?
Well, the 1 over
One.
is going to be 0.
1 over e is going to be 0. So this goes to 0.
So you only got 2.
Exactly, you got 2, which is equal to 2. And now these things are equal. So I can combine these two equations together. 24 over R2 plus 3 equal 2. Now I can basically find what my R2 is. 24 is 2 R2 plus 3, which is 2R2 plus 6. So 2R2 equals 24 minus 6. R2 is 24 minus 6 over 2, which is 9 ohms. So that's my first resistor value. I'm just going to box that one. And then all I got to do is take this one and then plug it right here to find my R1. R1 will be 21 minus R2. 21 minus 9 equal 12 ohms. So R1 is 12 ohms. There you go. Any questions on how we found the resistor values? No questions? Now going back to what you said basically is like, yes, you can use the equation to find the answers, but the reason I didn't is because I already did the part C and I knew that I had to do it anyway. So I just went ahead and wrote the equation like this. So that's determining the resistor values for R1 and R2. Now we want to find the inductance L, right? How would we find the inductance here? It's right here. We need to find this value. You got any clue for this one?
I don't.
Okay, it's okay. Now, yes. Yes, exactly. Yeah, but the intuition behind it is the reason we have a time dependence in the circuit is because of that inductor, right? Because that inductor has been storing current, right? And then as soon as that switch closes, it starts to like dissipate that current exponentially into the circuit, right? So the main reason we have a time dependence in that circuit is either an inductor or a capacitor, but in this case we don't have a capacitor, so we only have an inductor. So whenever you need to find an inductance in a circuit or a capacitance in a circuit, you have to already have that intuition at the back of your head that, hey, this has to do with a time dependency. So if I lead with that intuition that I have a time dependent stuff, I can kind of find my answer for that inductance. Now, this equation based on time right here, okay? This equation right here. You can see that it's the equation of the current that passes through this wire when time is bigger than 0. Is that correct? Is that equation that we just found? So that current is basically the current going inside of that inductor. Okay, and if I go back to these notes right here, and I scroll, these are the notes that I did yesterday. Here, there we go. The current inside of an inductor, the general form in terms of variable is that. So if I look at the variables here, I have I short circuit, IL0 plus, I short circuit, and I have this exponential right here. This exponential is RT over L. So that means to be able to find my L, I need to isolate for this. So now if I compare this equation to the equation that I have right here, okay, the rest in the front, it doesn't matter, right? All that matters to me is this part right here. So this exponential right here is going to be equal to this exponential. So we have e to the minus RTL over t. Let me check if that's correct. Yes. And that would be equal to the exponential that I have in terms of values, which is e to the minus 0.35 times t. Right? There you go. This is L on the bottom, and then this is T. Okay, so that means we have RT times T. This RT is not R times time, by the way, it's just R Thevenin. Just so I'll just write the subscript better. This is RT times time over L equal minus 0.35 times T. Minus goes away, the time cancels. So L would be equal to RT over 0.35. Now, what does this mean? This means that I need to find RT to be able to find L, right? I would have to find RT to be able to find L. Now, I need to keep in mind again that I'm working with a time range when it's very close to infinity. That's the range I'm working with. So that means I'm working with this circuit right here. I'm working with this circuit when time is very, very large. What I need to do is to find the Thevenin equivalent resistance at that point of the inductance. How do I do this? If I go to these notes, it says here, if you want to find the equivalent impedance, the only thing you got to do is disable all the dependent sources in your circuit, and then keep on combining resistors, and you'll find your RT, given that there are no dependent sources in that circuit. So I go in that circuit, there's no dependent sources, so that means I can just cancel this right here, and I leave this as an open circuit because I'm trying to find R Thevenin. So my circuit is like this. This goes away, so I'm going to have a short circuit right here. This is where the inductor is supposed to be, but this is where I'm trying to find the impedance or the resistance in that case. And then I have here R2. I have here 3. So if I want to find RT, all I got to do is keep on combining resistances. In this case, just series.
I think if we consider R1.
R1?
Yeah.
Because like you said earlier, it got disconnected, right? Right. So R2 is equal to 9. 9 plus 3 equals 12. So that means I have RT now. I can take that and shove that in there. So I have 12 over 0.35, which is equal to 34.29 henries. And this is going to be the answer for my inductance. Any questions on how we found this? No questions. I'll give you a question then. Just to kind of give a little bit more intuition. All right. Say I had here I of t, that equation still holds, right? The equation we have here, it still holds. But let's say that inductor is not here. This is a short circuit, right? Let's just say this is a short circuit, and that inductor is right here. Can I use the same approach? Why would you not use the same approach? That too, but imagine there's no, that it's still open. Just imagine it's open. Would you be able to use the same exact method? Yes, you would. Okay, you would. Now, let's just say the inductor is right here. Would you be able to use the right method, the same method? Why not? Yes, it's a different current. So that means you have to use this one to split it here. And then you find the current going through here, call it I alpha. Then this one is going to be the one you use. Yes, sir.
Did you explain current divider?
Current divider?
Yeah, in that situation.
In that situation, yeah, that's true. Let's see here. I'm just gonna do that in orange, and I'll make it a little bit thicker, so you know it's not part of the questions if I publish the notes here. Let's say you have an input current here. I'm gonna call it I big, right? Big I. And then that goes through parallel resistances here. Do you want the, it doesn't have to be grounded here. Do you want the quick answer or do you want the derivation? Quick answer. This is I1, this is I2, okay? I1 is R2 over R1 plus R2 times big I. I2 is R1 over R1 plus R2 times big I, okay? Yeah, this is current divider. I'll get to that. I'll do that one too. But if I look over here, is the I total is going to get split into two different currents, right? If I want to find I2, it's going to be R1 over R1 plus R2 times I total. I1 is going to be R2 over R1 plus R2 times I total. The way I remember it is if I'm trying to find, I have to make sure in my head that I know I'm working with current, right? I have to make sure in my head that this is current divided. So if I want to find I2, it's going to be the opposite resistance over the sum of both times the total resistance. If I want to find this one, it's going to be the opposite resistance, so R2 over R1 plus R2. So in this case, like I mentioned, right? Let's say you had a hypothetical resistance here, okay? And this is IT. Call that resistance value RA. So I want to find a value right here, I alpha. I alpha would be R1 over RA plus R1 times IT. We see how we got that? Okay, that's how it works. Let me just clean up this mess though, because it's not part of this question. So this is just current divider. I'll just do voltage divider right here. These divider equations is very important for you guys to actually learn it and then memorize it. Because when you go to electronics 1, it's a big lifesaver and it saves a lot of time in analysis. So here we go. We got a voltage here. Let's say this is a source. This is V1. This is R1. This is R2. And then I'm trying to find what V2 is. In this case, this is V2. Let me just call this V total. And then plus minus, this is V1. If I want to find V1, it's the opposite of current divider. So I look at the same resistor. Where's V1? V1 is right here. So watch the resistance in between V1. It's going to be R1. So R1 will be on top. R1 over R1 plus R2 times V total. And then V2 is going to be, what's the resistance between V2? It's just R2, right? If I look at the V2, the resistance in between these 2 points is R2. So R2 will be on top. R2 over R1 plus R2 times V. So that's voltage divider. Now let's get back on topic right here. We found the inductance value.
Can I see just?
Yes, sir. Actually, let me check the chat real quick. Okay, no questions in the chat. All right. Yeah, what's up?
A voltage divider. What if I added an extra resistor in parallel?
Where?
Right beside R2, let's say.
I'll do it right here. So you're saying you have this.
Yeah.
And I'm trying to call this the output.
Yes.
And this is the input. So this is R1, R2, R3, right? What are these two? It's in parallel, right? So I can say this one is R1 parallel R2, R2 parallel R3, right? So my voltage divider equation is going to be V out over R1 parallel R2 parallel R3 over R1 plus R2 parallel R3 times V in. You see where that comes from? Because if I combine these two in parallel, I basically go back to this case where R2 is just a parallel combination. So this is what will happen. Okay.
Well, 1% always divide by the equivalent resistance of the circuit.
Of the whole circuit. Yes, sir. Yes. Yes. But you have to make sure that it would be the whole circuit when your input voltage is that overall voltage source of your circuit, right? But if it's a random point at a random node, it won't be the whole circuit, right? If it has to be that, yeah, exactly. You get what I mean, right? Okay. Let me just write it well here. Yes. Well, I mean, if you look over here, is if you have two resistances in series, that's a clue for me to go for voltage. If I have two resistances in parallel, that's a clue for me to go in parallel, right? So current divider is associated with parallel, and then voltage dividers is just when you have two resistances in series. That's how I do it. And that's how it was designed to be used, right? These derivations work because these two are in series, and these derivations work because these two are in parallel, okay? Let's go to this one. Let me erase all this. Oh, okay. Any questions so far? Up until now? Okay. Now we have a little bit of a more tricky type of question. The reason behind that is because it's just complex analysis. But one good thing about this calculator, again, is it does it for you. So you can work with complex numbers and it's fine. So we got this circuit using the phasor notation and the mesh current method, find VOC, which is V open circuit, the Thevenin open circuit voltage of this circuit, okay? So we want to use mesh current to find VOC. Over here, if you look at the problem, it already gave us two open loops, two open nodes right here. So this is where my VOC is going to be situated. And I want to use mesh current to find that. When I look at a circuit like that, and I know it says use phasor notation, the first thing I want to do is identify what my frequency is. And when I say frequency, I mean angular frequency. So if I look at the circuit, where's the clue that tells me where my frequency is? Angular frequency. Yes, sir.
Besides T.
Yes, the coefficient of T, right? That's omega. Omega equal 500 radian per second. That's angular frequency right here. Okay, so that's the first identification. Now, why did I say that you need to identify this first? Is because, as you know, in the phasor domain, capacitances and inductances, they're going to be converted into something called impedances, right? And you got specific equations called J omega L and minus G over A omega C. So if you have your omega already for you, you can compute these values of the impedances and life is very, very easy. So what I need to do now is I can look at the circuit and see that I got a capacitance right here and I have no inductance. So that means if I call this XC, which is the capacitance, the impedance that is associated with the capacitor, it's 1 over J omega C or minus J over omega C. Now C over here is equal to 1 over 150 millifarad, which is 1 over 150 times 10 to the negative 3 farads. All right. Now I just take that value, I plug it in here. I'm not gonna do the number crunching. I'll just do this. This goes here, and then this goes here. And because of that, we have XC equal minus 300J. Any questions on how I found this impedance? No questions. Okay, beautiful. Now, one thing, this is my voltage source here. I gotta convert that into phasor notation as well. Are we all familiar with the phasor notation angle, amplitude, angle, phase? Like this, V angle phi, for example. So in this case, what's my phi? 0. Yeah. If you guys said something else than 0, I'd be very, very concerned because like that's like a main point of the course right here. So this would be converted into what? For example, what would be the phasor of this? 9 angle 0. 9 angle 0. So I'll just draw this circuit again in phasor notation, just so I don't confuse the hell out of myself because I always do. we have plus minus 9 angle 0. The resistor stays the same, 600. Here we have a dependent voltage source, minus plus. And then my capacitor, I'm just going to put it in a box here because it's not a capacitor anymore. It's neither a resistor, it's an impedance. And the way we represent an impedance in any course from now and going forward is by a box. So this is going to be XC, which is minus 300J. This is 2V, 300, ground, and then plus minus VOC. I think that's everything. Yeah, V is right here. Thank you. Okay. Now my I1 and I2. I remember I went to the class with Prof. God. I took it with himself. He said that when you go in phasor domain, one thing he looks for is the notation you use to find the values you need, right? So you go from small letters to capital, right? So when you're writing your currents here, instead of writing small I1, I would explicitly write it like this: big I1, big I2. This is a way for me to show him that I know that I listened to you in class and that it's a capital and not a lowercase. So now that I have this, I have two meshes, I have two unknowns. That means I need to write two equations. So I'll just do this here. KVL at I1. Now, if I follow this this loop, there's a loop right here. If I follow this loop, it's going to be minus 9 times 9 angle 0, sorry. So minus 9 angle 0. Again, current is going to go through the positive end. So plus 600 I1 plus V equal 0. That's my first equation. Now I need to find my second equation, which is KVL at I2. Okay? And this is equal to minus V minus 2V. Why? If I follow this loop, it's minus V minus 2V. And then again, this is plus minus 300 I2 equal 0. So these two equations, are there any doubts, queries, concerns about how I found them? No. Again, if you found this equation is incorrect, that's like, if this question is out of 10, that's probably like 8 out of 10 already. So just write your equations down. Maybe not for this one, because this is phasor. He wants to see a complex analysis done properly. So I would say it's worth about 6 out of 10, the equations themselves. Now, as I mentioned earlier, I'm doing KVL. So if I look at my two equations, I need my unknowns to be two specific stuff, right? What are my unknowns supposed to be?
I1 and
I1 and I2. Anything else has to disappear or be written in terms of I1 and I2. So if I look over here at this equation, the only thing that annoys me is V, okay? So I need to find V. How do I find V?
So it's going to be I1 minus I2 times the impedance, which is minus 300J.
So minus 300J times I1 minus I2, that's perfectly right, okay? Now I'm just going to clean up this equation right here because I can combine these two into one term. I have minus 3V plus 300 I2 equals 0. All right. Now I'm just going to call this equation equation A, equation B. I'm working with equation A first. I have minus 9 angle 0 plus 600 I1 plus V, which is minus 300J I1 minus I2 equals 0. So this is my first equation. And I'm just going to clean up this equation a little bit more. One thing I can do is realize that this value, is it a complex number?
No, just minus 1.
Minus 9. So that means I can take this and shove it to the other side of the equation, right? I can do this. So I can have 600 I1 minus 300 J I1 plus 300 J I2 equal 9 angle 0, right? Now, one thing I can do is I realize that, hey, I1 is common. That means I can factor it out. I can factor out my I1s. So I have 600 minus 300J multiplied by I1 plus 300J I2 equal 9 angle 0. Okay? That's the first equation I'll box in orange here. Again, I'm just trying to write it in the form where I have I1 multiplied by something plus I2 multiplied by something equals something. The second equation is right here. I have minus 3 times minus 300J I1 minus I2 plus 300 I2 equals 0. Again, in this case, V right here, where I found it is from this one. I just plugged it in here. Minus minus cancels out. So I have 900J times I1 minus 900J times I2 plus 300 I2 equals 0. Again, I notice that I2 is common, so that means I can factor it out. 900J I1 plus minus 900J plus 300 I2 equal 0. Let me just check if I'm on the right track and then there's no mathematical mistakes going on. Okay, this is clear? So I'll just write, now I have two equations right here, two equations, two unknowns, where my unknowns are basically what I want. Okay, so I can isolate for one of them in terms of the other. Here I isolate for I1. So I would have that 900J I1 equals minus 900J plus 300 I2. All I did is took this and then brought it to the other side. So this is equal to 900J minus 300 times I2. And I1, if I divide both sides by 900, I get this. Now, all that's left for me to do is to simplify this using my calculator. All I can do is just put in my calculator. It's going to give me a simpler value here. So if I do this, it's going to give me 1 plus 1 over 3J times I2, and I'll box this one in green. There you go. Any questions on how I find that? How I found that? No questions? Okay. I'll just take I1 and I'll plug it in the equation A right now. Let me just erase all of this. Okay. So I'll take I1 and plug it in here. So I have 600 minus 300J. I1 is basically 1 plus 1 over 3 times J multiplied by I2 plus 300J times I2 equal 9 angle 0. Now I have something times I2 plus something times I2 equal 9 angle 0. Again, I can basically isolate my I2 out, and everything that's inside is 600 minus 300J times 1 plus 1 over 3J plus 300J equal 9 angle 0. If I want I2 alone, it's 9 angle 0 divided by whatever the hell I got here. So 600 minus 300J, 1 plus 1 over 3J plus 300J. If I put that into my calculator, it's going to give him a nice simple answer, which is I2 0.0119 minus J 0.0034 amperes. Now, the good thing about this calculator as well, if you go, you can write it into polar form. Polar form means amplitude, angle, phase. So if I do that, I get that my answer is 0.0012 angle minus 16 amperes. So that's I2. I'll box it. If I want to find I1, all I got to do is take the value of I2 and plug it in here. So I1 equal 1 plus 1 over 3J times I2, which is 0.012 angle 16. This is negative 16, by the way. Negative 16. Negative 16. And then if you plug that in the calculator, you get 0.013 angle 0.043 degrees. That's in ampere as well. And if you want it into regular complex form, it's just 0.013 plus J 0.0000566 ampere. Any questions? You can do it when it's any angle. You could always do it. The reason I did it to be more general is because it's not multiplied by any voltage or current. It's just a value by itself. It's like a complex constant. And the right side of my equations, me personally, I always like to keep it constants, whether it's real or complex. Because what that does, it just gives me whatever I got here. It's like in linear algebra, it's a linear combination, right? Right? This is a linear combination. So you got I1 and I2, they're linearly combined to give you something, right? But because the coefficients of I1 and I2 are complex, that means the linear combination of two variables by complex coefficients by nature is going to give you a complex answer, right? So that's why I write it this way, just to go back to because I've done a lot of practice for this course, and the way that I found that I do it and I don't do any mistakes is when I do stuff in that fashion. I do everything according to plan, variables on one side, complex or real constants on one side. It's very easy for me to follow, and that habit kind of led into future classes where I was very happy that I started this early on. Questions? Yeah.
So you're saying all the stuff that you're not showing, it's because you can just punch it into the calculator.
Yes, and it will do it for you magically. Yeah, it would just do it.
All the angles.
Everything you want. Yeah. Yeah, it will give you the answer in this form, but if you go how to say this? If you go in complex mode, you can do amplitude angle thing, and then when you press enter, it's gonna give you give it to you. Yes.
Save you lots of.
It will save you lots of time, and then it's probably gonna be correct if you wrote your equations correctly, and it's gonna save you in future classes too, because this phasor notation you will use in electric machines and power systems that you take in the second semester of third year. You will use that in electromagnetic engineering as well. It just keeps on coming. Phasor is something very, very important. So I would say it's a good investment to get one of these, honestly. Any questions here besides these stuff? So like the questions about the problem here. I just found my I1 and I2, but the question wasn't about finding I1 and I2. It was about finding VOC, right? I want to find this value right here. But if I look at the circuit, VOC is in parallel with this resistor, right? And what's the current flowing through that resistor?
It's 300 times I2.
300 times I2 is equal to VOC. So again, I can basically just use Ohm's law to find that value. So I'll just write it here to be explicit. VOC equal I2 phasor times 300. So that's going to be equal to 0.012 angle minus 0.278 times 300. So VOC equal 3.46 minus J 0.988 volts. So my calculator gave me in this form. When I converted the form, it gave me this one.
What's the I2 was 0.0112 angle minus 16?
Oh yeah, you're right, minus 16. This value again is a mistake, but it's a mistake that's not totally a mistake. You know what the mistake is? I was in radians. Yeah, and I was comparing my solution. I was like, yeah, something not adding up, but the coefficient that the amplitudes are correct. So make sure your calculators are in degrees when you're doing these types of questions, okay? Because otherwise your phase is going to be off. Unless you explicit mention that you're working in radians, which is fine. But otherwise, just work in degrees because it's much, much easier to spot. Because your graphs are like this, it's much easier for you to spot phases differences in degrees than it is in radians. So any questions on how I got VOC? So I'll just box it again here. Okay. Now before we move on, we're just gonna take like a quick 5 to 6 minutes break, washroom break, whatever, if you have to, and then we're gonna keep on going.
Yeah.
We could just go to the bookstore, like the
Campus.
It's still there, yeah. It is still over there. Let me check the chat. No, it's just a break time. Même on arrive. Yeah, that's the one.
That's it.
Yeah.
They said that
Could you share the sheet you made on Discord? Oh yeah, yeah, because people are wanting it. I think when I'm done these, I'm just gonna save it as a PDF and then post it on Discord after. Also, this meeting is being recorded right now, I think. Hope so. Oh yeah, it is being recorded. So if all things go according to plan, it will be posted on the IEEE YouTube channel as well. So what's up? Yes, sir.
What's the function you use on your calculator to convert it from like the Poland?
Yeah, so if you
And
if it's like 2 plus I3, right?
yeah,
So this is a complex number. I go second function complex, and then this is R angle theta.
Okay.
So I just press enter, and I press enter again, and then this is the amplitude angle. If I press enter again, it's just gonna give me amplitude here and then phase. Yeah. You're supposed to do that too?
I mean, you're not getting complex. I'm going to assume it's able to.
Let me see. Can I see?
Okay.
What's your name, by the way?
Lightning.
Lightning?
Yeah.
Lightning, like lightning.
Yeah,
For
like
real? Yo, his name's Lightning. That's really sick, bro. What the
Thanks.
hell? Okay.
What's your name? I didn't get it.
Ayush.
Ayush?
Yes, sir.
Nice to meet you.
Nice to meet you too. Let me see here. Don't think.
Damn.
I don't know. But I see this. I
Yeah,
see
that's what I'm
this.
saying. Like, it's capable of putting into
Maybe you can do
Complex
some research on that, like on YouTube or something like that.
yeah.
Yeah.
Oh well.
Can you try to figure it out?
What? How to do matrices on this?
No.
No.
Oh, do you have the same one?
Yeah.
Can yours do it too?
Oh.
You electrical engineer?
Yeah.
Yeah, good.
You too?
Yes, sir.
How is it?
Electrical and physics. I'm in 4th year right now.
How was electricity E&M?
E&M with Michel Godin. Is it who you have it with?
Yeah.
It's gonna be a chill life if you go to every lecture. He's a very good prof.
I'm happy to hear it.
Yes, and also
Physics, you can do an angle. Well, I'm really complex, that's fine. I think that's switch my one to complex. Two.
in physics as well.
It's not even-
electrical and physics. What year?
I'm in the second.
Yeah. How do I switch from?
You in the French section? English. So you just took like waves and optics and mechanics too?
Yeah.
I
Mechanics exam Sunday.
Changer.
I heard it's like
Yes,
very similar to past assignments for with Peter Piercy, right?
Piercy, yeah.
Yeah.
It's, I don't know,
Oh, yeah.
he puts a
Okay.
lot
Oh,
of
shit.
twist on it.
So
Yeah?
if, for example,
That's good. I mean, You got modern next semester, I think, modern physics
It's Piercy as well.
with Piercy. Yeah, his midterm for that was hard.
Yeah, I thought that.
That's why I had to lock in for that final. Yeah.
What's your passage?
No, same with the.
Yes, sir.
the weight
Oh, it's fucking there.
transfer.
I'm actually glad.
What's your name?
Stefan.
Stefan, nice to meet you. Ayush. Yeah. What's up? Oh yeah, no problem. I love doing it. This is the whole reason I joined IEEE to be able to do this. Yeah, I want to give back.
Nice.
Yeah, I'm gonna do it for some winter classes too, like electronics 1.
Hey, let's go.
Yeah, and I'm trying to get people to do for the physics classes as well.
Huh?
So we'll see how that goes. No promises for now.
Yeah.
Electronics 1 for sure. I'm doing it. Yeah. Do you know Elise? Yeah. Okay. I think she used to be in that one too, but I'm trying to get her to teach because she's really good at teaching that as well. Yeah.
Okay.
Yeah. Katie's our day one. We've suffered together.
No, I'll bring it up.
Oh, yeah, for sure. No, that would be very helpful. Yeah. Okay. Someone can be right on time, man. Yeah.
It's a dumb mistake that's happened. You have electronic.
That's perfect. More questions.
That's a good point. We got like 30 seconds left in the break. Can you pass me a cookie?
Well, yeah, like, email doesn't pull another, when you put a multiple choice question.
He did that?
Yeah, there were 4 questions, one of them was you solve it, and then there were find equations, and then it was a multiple choice and 6 options.
Yeah, think option.
Negative grades?
It was, no.
Yeah, like the simple thing you've done, made the program one, like 2 lines short.
Oh, yeah, bro, like.
So like if you messed it, like if you messed like one thing up, like you would get like 0 out of 20.
Yeah, I sent the drawing and then I.
He's when I took the class with him, he was so nice. He's like, he was such a good prof. Like everything was on point. He made me realize, I'm like, yeah, I love electrical engineering just because of this class. But then I took a 4th year class with him. He showed his true colors, man. What's up?
How are you, man? How did you record it? You record this?
Yeah, I'm recording on Teams right now.
When do you put it? When you upload it?
It's gonna be on the IEEE YouTube channel.
YouTube channel?
Yes, sir.
Your
Electrical physics, yes.
bachelor, master,
Bachelor's.
4th year?
Yeah, 4th year, sir. Yeesh. I'm still trying to survive here.
Which one you think is harder? Electromagnetic engineering?
Electromagnetic?
Hard. Electromagnetic.
Yeah. Honestly, all of them are hard for me, man. There's no class that I found easy. Personally.
And signal.
Electronics 1 is a big jump from circuit theory. It's a big jump. Very, very big jump.
Electronic 1
Electronics 1.
is harder than this.
Yes, much harder.
Electronic 1.
Yes.
Electronic 2?
Much harder than electronics 1.
Really?
Yes, sir.
Circuit theory 2?
Circuit theory 2, with Hilmi, I found it hard to follow along. Just because of his accent a little bit. All right.
When do you upload?
I don't know yet. Yeah, after the session.
IEEE.
Yes, sir.
Probably takes the.
How can you say that third?
All right.
I think that's.
All right, we're gonna get back on topic and then follow along with the other methods right here. Okay. So the first part of the question, it asks to find V open circuit. The second part of the question is gonna ask you to find I short circuit in this case. So again, same process. The only thing here is in this circuit right here, V open circuit, you find it when your output of the circuit is open. So you just find that voltage. For the second case, you're gonna short that circuit and then give ISC as current into the circuit. Okay, that's how you're gonna do it. So I'll just go ahead and do that. I'll copy this circuit again here. So for right now, when I'm doing these questions, I'm writing them out and I'm trying to work through all of them. Now, just because I don't want to run out of time, I have the other answers already written up. So I might just point it with my laser and go through the math and explain the concepts as we go. But I'll try my best to write everything along as I go. And if I feel like we're gonna run out of time, then I'll go a little bit through the solutions and read through them as we go forward. So here, this is gonna be shorted. It's gonna be shorted, and then ISC is gonna go into that circuit right here. Now, there's a very nice change that happens to this circuit as I short my output and give ISC into the circuit. What happens here? The resistor disappear. So I'm just gonna do this. Oops. Let me just leave it here. Okay. Again, it says explicitly in the question, use mesh current. So I'll do that again. I'll do my KVL at I1, which is -9 angle 0 plus 600 I1 plus V equals 0. KVL at I2, which is -V minus 2V equals 0, right? We see this? I'm probably going to run out of space. Hold on one sec. There. So if I use my second equation, I find that -3V equals 0. So what does that mean? V equals 0. Okay, V equals 0. Take that and plug it in here. This goes to 0. So my equation is -9 angle 0 plus 601 I1 equals 0. I plus my 9 angle 0 on both sides. I have 600 I1 equals 9 angle 0. I1 is 9 angle 0 over 600. And if I plug that into my calculator, you guys are already seeing how much of a life hack this thing is. Just, oh, is it not? Okay, it's right here. Okay, I1 is equal to 0.0 plus J0, which is equal to 0.015 angle 0 in amperes. I'll just box that. So that's my I1. And then I2 is equal to the same thing over here. Why would it be equal to the same thing? I kind of skipped some steps here. But if you look at this voltage right here, what's the equation of that voltage? Well, no, I mean, in terms of the mesh currents, yeah, it is 0, but in terms of mesh currents, it's going to be the impedance 300 times I1 minus I2, right? Minus I2, which is equal to 0.
So
Right.
that means that I'm of 0.
Yes, which means I1 equal I2, right? Which means that this answer right here is also valid for I2. 0.015 angle 0. Now, my question was never about finding I1 or I2, but it was finding ISC, which is short circuit. Now, if I look over here, this I2 is defined from the problem. If I go up, there's the problem, right? In the circuit, it is clockwise. That's the convention to go clockwise.
Right.
But when I drew my ISC, I said that the current is going this way. So I got this going on right here. So I2 will be equal to minus ISC. I just chose to. I could have drawn it in the other direction. You could do that too. Honestly, you could do that too. But it's not a wrong answer, right? Because current is, you could have minus current. But if you want to do that, you can do that too. It's all about being consistent with what you already did in the first place. Yes, sir. Ah?
Which capacitors?
Oh no, I thought you meant that in the question. Why is it 0?
Yeah.
Okay, that comes from the KVL at I2. Let's go through it step by step, right? My second KVL is right here, correct? Minus V, what the hell? Okay. Minus V, minus 2V. If I keep on going, there's nothing here. So that's my KVL, it's equal to 0. Minus V, minus 2V equal to 0, right? That's my KVL right there. Okay, so that means minus 3V equals 0. So what does that mean? V equals 0, right? It's not given, we just proved it. Is that clear?
Yeah.
Okay. So this is my I1 and I2. And like I said before, I2 equals minus ISC, which means that ISC is the same answer with a negative sign in front. So minus 0.015 angle 0 in ampere. So this is ISC. Now the next part of the question. Oh, delete this. Okay. Next part of the question, it says, from part A and part B, find the total Thevenin equivalent of the circuit. Oh my God. Okay, there we go. So this is voltage, resistance. So what it's telling us to find is find VOC, which we already have, by the way. We did this in the first part. The only thing we don't know is RT. Okay. Now, one thing to keep in mind here is this current flowing through the circuit right now, right? Because VOC, the whole point of the Thevenin circuit is to give that current, that the circuit the same amount of juice and the same amount of voltage, right? So over here, if I replace this circuit right here with my Thevenin equivalent, if I replace it with Thevenin equivalent, right? It's gonna look like something like that. So all of that is gonna be replaced with my resistance and my voltage right here. This is VOC, resistance, right here. Everything right here comes into that. All right. But so now if you're looking at the circuit, I said that ISC is actually going up, right? This is very important to pay attention. So this is my source, this is my resistor over here, but the current given in the problem is actually going this way. So I can't use the value of ISC that I got to flip that value to follow this line. So this is when we do what you did. All right, you flip it to follow the convention of the circuit. It would be wrong to do it the other way, because we'd be saying that the current is going in the opposite direction when Thevenin says that the current is going up. You have to follow the circuit convention for that. Do we understand why I said I would flip it?
So for Thevenin, you can't flip the voltage source, because if we decide that ISC is going up, then
Yeah.
it should be minus plus.
Exactly.
You can't do that.
No. That's not what Thevenin is, right? Because your bottom is grounded here, right? Your bottom is grounded here. So because if you flip it, that means you're flipping your ground as well. But it's another story if you put the ground on top. But that's just you redrawing the same thing upside down, right? So, hey, I'll go through that again. So what I want you to realize here is these two terminals right here, these two terminals, and then this circuit is going to be my resistor, my source. This is Thevenin, right? This is Thevenin. Now, the current flowing here is I2, right? I2 is flowing here, I2, not ISC. ISC is flowing this way. It's the opposite direction. I have to follow this direction because my positive side of the voltage is right here. So that means current is flowing into the circuit. So that's why I'm not going to use the ISC value that I have here. I need to flip it for it to go down to be able to follow that convention. It's just a sign change. Questions about that?
It matters.
The direction of the current matters. That's why we have plus and minus. Yes, the direction matters. It doesn't matter where you put it initially in your circuit. It matters when you're doing other steps in your circuit, you realize that the direction initially was wrong. So you have to flip it to match the circuit, right? The whole point, the whole thing that I got minus here is just saying that I chose the direction to be wrong. So I just got to correct myself. Yes. Mm-hmm.
If you have dependent, just put imaginary independent current source from here.
Imaginary independent current?
No, we put independent current source to find R Thevenin. Just one anchor.
Yes, if you have dependent sources in the circuit, yes.
So the direction of that independent doesn't.
It doesn't matter really because if you it doesn't matter because you will get a negative answer in your current, right? So you could just again do the same thing.
But
The-
here I should say
The direction matters because you're doing Thevenin. Because you're doing Thevenin. Thevenin, it's like Thevenin is defined in a way, right? You got to respect that way it's defined for. But when you're just solving a circuit on your own, you can do whatever you want. What's up? That's not, no. I'm just saying that if this is my Thevenin, yes. Oh, here. Yes, I2 is equal to I1. But that's just because V equals 0, right? So this voltage right here is going to be this times I1 minus I2, okay? Yeah, exactly. There's no voltage there. No, there could still be current going on here. There could still be current. It's just the difference in the current is 0. It could not be, you know?
It's basically just a wire.
Yeah. No, not even.
Well, if the voltage.
Yeah, no, you're right. If it was a volt, yes. If the voltage is 0, it's just going to be a short circuit. Yeah. So exactly, your short circuit is a load, right? So that's why I got ISC here. And this is why when I do RT is VOC over I2. Do you understand why I wrote I2 there and not ISC? Because I flip ISC, and when we flip ISC, it's the same thing as I2. So I have RT, I'm not going to crunch the values. RT will just be equal to, this is not RT, by the way. This is complex, so this is Z. ZT. So 240 angle negative 16 ohms. Question? Let's move on to the next one here. Okay. So this is okay. I think we have enough time for me to go through every single one of them and finish on time here. Okay. Now this is a circuit where you're not mandated to use any of the methods he tells you. You can do whatever you want. So what's the step one that I just talked about to do when you're dealing with time dependency in the circuit? You need to identify one thing.
So the sources, and then we can just transform it to power form.
Yeah, but there's one thing before that as well. Frequency, yes. Because everything we're doing right now is frequency response. What's my frequency in this case? 10. Now, if he was being a very conceptual prof and asking a question that's worth 20 marks with no analysis, which because he did that in the midterm, I'm starting to think he might pull that on the final. He could give you an unsolvable question and then people would attempt to solve it and it's completely wrong and you lose like 20%. It is possible with these kind of circuits here. Here, omega is 10, right? But if in this case you had 5 cos 20t, you can't solve this problem.
Well, you do speckles here.
I mean, no. You have two different omegas. You have two different frequencies.
that's why you do superpose.
Yes, exactly. You will learn in third year. Yeah. So that's the thing. So if he changes your omega in two different sources in that circuit, just write unsolvable. We'll learn in third year, basically. And that's worth 25 marks right there. That's worth 25 marks. Yes, sir.
Can you also have multiple choice?
Yes, I was hearing about that earlier. Yeah. So do you guys understand the point here? So I check my omega. So that's why I always say is like when you're doing this question, check your omega. If the omega is the same, that's your green light to keep on going. Here my omega is the same. Okay. Now all I gotta do is write it in phasor. So it's gonna be 6 angle 0. There's gonna be 5 angle 0. There's gonna be J omega L, which is J. Omega is 10, L is 2, which is equal to J20. This one clear? Okay. This is going to be minus J over omega C, which is minus J over 10 times 50 times 10 to the negative 3, because I want to correct it to farads. So what do I have here? I want to plug it. It's minus J2. Okay. So now I'll draw the circuit again. If I draw the circuit again, I have something like that. Resistor. And then this is J20. This is my current source, 6 angle 0. Ground on the bottom. This is ZC. 5 angle 0. And then it's straight up connected to ground. Let me bring this down a little bit more. Okay. So I chose node voltage to solve this question. The reason behind it is because, well, I mean, one way to say it is just I've taken so many circuit classes so far that I've solved so many circuits that when I look at a circuit, I'm like, okay, this is probably going to be the most efficient way to do it. Sometimes I'm wrong. It is the longer way, but this kind of intuition kind of grows into you that, hey, when you look at a circuit, okay, this is probably the best way to do it to save me time and to find the answer correctly. So I'll use, it's just experience. It's just by experience. I don't, I've never really heard that. There's no rule. Like, I mean, there's no really good rule for you to gauge that. All I will say is circuits is a language. Like, you know, you got programming languages, electrical circuits are languages as well. So when you look at circuits over time, you'll be able to already know the answer without doing any analysis. That's the goal of the first couple of years of electrical engineering, is to get you to be able to read a circuit, not to analyze it. You should be able to read it. You read it and you'll be able to know here. For example, I look at a circuit, I'm able to say, okay, voltage divider here, current divider here, parallel. So it's all going to simplify. You see what I'm trying to say here? It's just through that. So that's why I chose to do node voltage here. I don't really have a reason. I just know it's the shortest way to do it. So this is V1, which is defined in the question. I call this V2, but this V2 will be equal to whatever this source is going on here, which is 5 angle 0. Okay, so now I'm going to do a KCL at V1 here. KCL, I'll just do this. KCL at V1. Also, one more thing, just to kind of back up my point. This guy right here took the class with me. There are circuits I solved that took me 8 hours because I didn't have the background intuition. And he did it without any analysis sometimes. He just looked at it and he was like, okay, this is the answer. And I asked him how he got it. When he explained it, he was just like, okay, he just saw what I didn't see. For example. So I got 6 angle 0 equal V1 minus 0 over J20 plus V1 minus V2 over ZC, which is minus J2. Is that clear? It's a node voltage equation. Any questions about that? No questions? Okay. So that's one thing. V2 is just 5 angle 0. So I'll replace it and write 5 angle 0. Now, as you can see, I have one equation, one unknown. So it's simple, right? One equation, one unknown. But now think about it. If I had two meshes here, I would have two equations, two unknowns. So I just saved myself like a lot of algebra. What's up? Yes, you're right. You're right. I forgot to write the value here. You're right. It is J20 plus the resistor.
Could you combine?
You could do that. So I'll just split the denominators. I have 6 angle 0 plus V1 over 10. Oops, equal 10 plus J20 plus V1 over minus J2 plus minus 5 angle 0 over minus J2. These things become positive. These signs, I can flip them. I'll just create a new page. And I have 6 angle 0 minus 5 angle 0 over J2. And then I have V1 over 10 plus J20 minus V1 over J2. Now I have V1 in common, so I can take it out. V1 times 1 over J plus 1 over 10 plus J20 minus 1 over J2. And now I can divide by this on both sides to find what V1 is. So V1 will be 6 angle 0 minus 5 angle 0 over J2 divided by 1 over J plus, no, 10 plus J20, 1 over J2. Again, I plug this in my calculator, and it's going to give me minus 0.419 minus J 0.491. This is volts. No, wait, this is a voltage. This is a voltage. It's not this. It's this one. It's going to give you this value in volts. So now that I found what V1 is, I can easily find my currents, because over here, this is I1, and it's going to be I2 right here. So I1, if I go right here, this is both in series. So it's going to be V1 minus 0 over this, which I already know what V1 is. So 5.63 minus J13.3 over 10 plus J20, which adds up to minus 0.419 minus J 0.491 ampere over, or in phasor form, 0.65 angle minus 130.5 amperes. So this is I1. Okay. Now to find I2, if I go over here, I2 flows right here. So V1 minus V2 over this impedance is going to give me I2. Is that clear? It's Ohm's law. V1 minus V2 over this impedance gives me I2. So I2 is V1 minus V2 over ZC, which is 5.63 minus J 13.3 minus 5 over minus J2, which is 6.65 plus J 0.315, and that's complex form, and that's equal to 6.65 angle 2.7 amperes. And that's I1 and I2. So the question has been answered. Find I1 and I2. Has it been answered though? I found I1 and I2. Yeah, exactly. So I would lose 1 mark if I just answered like that. I want to convert it back to time. So I1 as a function of time is 0.65 cos, and my omega is 10. 10t minus 130.5 amps, and I2 is 6.65 cos 10t plus 2.7 amps. Questions?
Out of curiosity, for the forces, what if instead of cos, you put sine?
It's you have another minus 90 degree to worry about, right? Because right, this is a sine, and then this is a cos, right? So to bring the cos to the sine, you have to minus 90 degrees, right? If you want to bring the orange curve right here, minus 90 degrees. So if you're using sine, it's going to be plus 90 to bring it back to the cos. So you just have to worry about that. But all phasor notation in electrical engineering has been defined in cos. So if you use cos, you're more likely to be safe that you're not going to forget the 90-degree shift. Okay?
Frequency would be the same.
The omega? The omega stays the same. Yes, because if you look at the period here, it's the same period. I know the drawing is kind of bad, but it is the same period. Okay, now let me erase this. Okay,
All of them is. Give the answer back to sign. Or it's not a risk we should take.
you can do it. You can do it. Yes, if it's everything in sine, you can bring it to phasor and work through everything the same, and it will give you the same answer, right? Just because the frequency is the same. Okay, but if you have one in sine, one in cos, you got to make the right adjustment. It's your choice. You can bring it all to sine, which I wouldn't do because there's too many 90 degrees there. I'm going to mess up. So I'll bring it back all to cos. Okay, but that's a very good question. It says here, the next question, find a complex power delivered by the two independent sources. So if you look at the circuit, you got two sources. You got a current source here, and then you got a voltage source here. You want to find the complex power delivered. Now, anyone remembers the complex power equation? What is it equal to? Yes, sir. Yes, it is. S is equal to half VI conjugate. Okay. So my two complex sources I need to find is 5. For the current source is 6 angle 0. So I'm just going to subscript that 6 angle 0. And then the other one is the voltage source, 5 angle 0. These are the two I need to find. Now, when I have the currents here, it's very important not to use any current or any voltage in a circuit. You have to use the currents and voltages, voltage across that source and the current going through that source. Okay, so if I go to my circuit, I got this. So the current going through that source is this value right here. And the voltage through that source is V1. Right, okay? So I'm just going to write it explicitly here that I'm going to have 1 over 2 times V1 multiplied by the current going through that source, which is 6 angle 0. Okay?
Isn't it the conjugate of 6 angle 0?
But I mean, since this one is just a real number anyway, so it's going to be equal to. But you're completely right. I would still put the star on there. So 1 over 2 times V1, which is 5. We calculated V1 before. So I can just use that value times 6, which is 18 plus J, 39.9. What's the units of complex power? Volt ampere, yes. So now for the second case, I look at the source again. The current going through that source is I2, right? And the voltage through that source is that. It's the source voltage itself. Now, one thing to keep in mind is when you have a voltage source, right? When you have a voltage source, it produces current, right? It's trying to give current into the circuit. Over here, the positive sign is up. So that means my current should go like this. So exactly, that's the point I was trying to make. So it's important to look at the circuit and also respect the signs of that current, right? When you're solving that circuit on your own, it's fine. You can get the current wrong. It's fine. It's just a negative sign. But when you're using the current equations to find power, you got to respect the way the sources provide current into that circuit, because according to theory, the current will flow into the circuit. So I need to change my I2 to minus I2. So it will be here 1 over 2, 5 angle 0, which is the source voltage, minus I2 conjugate. Now if I'm crunching my numbers, 5 minus 6.65, which is I2, plus J 0.15, that complex conjugate. Now let me just check something real quick. I want to see if that answer, just what I got here. 5 over 2 times minus 6.65. 6.65 minus 0.315. Yep, 16. So I have minus 16 plus J 1 volt ampere. Okay, so this is the power delivered into the circuit by the voltage source, and then this is by the current source. So voltage source, and then this is current source. Is this clear? So the only thing I would say to remember when we're finding delivered power from sources is make sure you're respecting the voltage and current configurations, right? The directions of them. And make sure the voltage is across the source itself, not something else, and the current is the one going through the source. Now we want to find the complex power absorbed by the three passive elements. So if I look at the circuit here, we have 1, 2, 3 passive elements. So we want to find the current that those elements are going to consume from the sources. That's one way to say it. So we got the current from the 10 ohm resistor, right? So one thing before I move on, complex power is equal to half VI conjugate. Is that correct? Okay. Now one thing I wanna derive here and give some intuition behind, because that's gonna save you a lot of time. What is voltage equal to? Just in general, like easiest equation ever in. Yeah. But in this case, we're in complex, so it's gonna be ZI, right? So if I take that, I plug it in here. I have S equals 1 over 2 ZI times I conjugate. So I have 1 over 2 ZI conjugate times I. What is that equal to? No, from linear algebra, it's just the modulus, so absolute value of I squared. Okay? So that means Z, S equal 1 over 2 I squared. So that's one equation I'll box. So why am I doing this right now? Because sometimes I just know the current going through the load, right? If I have an impedance, it's not necessarily true that I know both the current and the voltage going through that load, right? I might just know the current, I might just know the voltage, but for sure I'm going to know what the impedance is, because in the circuit, in the problem, it's going to define it, right? It's going to tell me this is an impedance of this many ohms. I know that. So I want to derive equations where I can just plug it. And if I remember these going into the exam, or if I don't, I can come to them by myself because I understand the intuition behind it. So that's number one. That's one way to remember, because what I got here is just the impedance that the problem gives me, and I is the current that I calculate in the circuit, for example. But now, if I have V equals ZI, I want to isolate for I. So I would be V over Z. We all agree with that? Yeah? So I'll take that and I plug it in the equation again. So I get S equals 1 over 2 V times V over Z conjugate. Right? So I have 1 over 2 Z conjugate. So let me write this better. 1 over 2 times 1 over Z conjugate V conjugate V. This is V squared. Okay? So this would be equal to 1 over 2 times 1 over Z conjugate times V squared. So now I have two equations. 1 over 2 Z conjugate times V squared. Why is that? Why did I conjugate the Z? Because the Z can be complex as well, right? It could be complex. So now I have two equations. Now, if I have a load and I know the current through the load, I can find the complex power this way. If I have a load and I know the voltage to that load, I use this one. So now I'll find my power through the resistor right here. Now, if you look at this equation right here, and not equation, but a circuit, what's the current going through 10 ohms? It's I1, right? So that means I can use this, which is S equals 1 over 2, Z is 10, and then I go find where I1 is. I1 is right here. What's the amplitude? No, what's the amplitude of I1? Basically, the absolute value of I1 is basically this number right here, right? Amplitude, angle, phase. So I can use it straight away. IS squared over 2. Yeah.
Is equal to I squared divided by 2 times real part of it.
Yes. You can do that. It's the same as these, but these are much faster. These are much faster because you don't need to calculate both the voltage and the current. If you know one of them, you have the answer. That's why I use these ones. That's why I always use these ones. So if you put that into your calculator, you get 112 volt ampere. So that's one of them. Now, if I want to find S, this is through the 10 ohms. Now through the inductance, again, the inductance is just below the resistance right here. So it's the same current going through it. The only thing I need to change is the value of Z I'm going to put in. So it's going to be 1 over 2 times the value of Z, which is J20, but the current stays the same. And if I put that into the calculator, I get J 4.2225 volt ampere. That's the second value of the power that I'm calculating. Let me create a new page. All right. Last thing I got to calculate is through the capacitor, 1 over 2. If I go up and I look at the capacitor, all I got to be careful is ask myself is what current is flowing through that capacitor? Which one is it? It's I2, right? So I use the value of I2, the amplitude of I2 instead. So if I go over here, amplitude of I2 is 6.65. Okay? So minus J2 times 6.65 squared, which is minus J 44.23 volts ampere. Now I'm just going to box that as well. Any questions on how I found these powers? Why are we not multiplying? We're just dividing by it? Yeah, I'm using the current equation. Okay. Yeah, because I know the current. But if you use if you do V1 minus V2, you calculate that voltage. And then if you want to say for example, say you didn't know this current, right? But you can find the voltage across these across the capacitor, right? It's going to be V1 minus V2, right? It's going to give you a value, but it's going to be a voltage value. So if you're using that voltage value in here, that's when you conjugate it. Okay? Yeah. And you divide instead of multiply. Why you divide? Because current is V over Z, so the Z comes on the bottom. Okay? So this is the power consumed. This is the power delivered. Now, here is just saying, I'm not gonna rewrite this. It says justify the conservation of energy theorem. What does that mean? It just means that the sum of the power you gave into the circuit has to be equal to the sum of the power that the elements ate from the circuit, basically, right? It's like, if you give me 500 calories to eat, the calories gone from the table is now in my stomach. All right? Same thing with the source and the circuit. So I calculate S delivered total, which is from the sources that I calculate in part A. I take these values, these two, I add them up, all right? And I take these three values, I add them up, and these values have to be somewhat close to each other. They're not going to be totally accurate like that. I rounded up a lot, but it has to be very, very close, right? And if they're very, very close, that means you have conservation of energy. You did not do a mistake in your answer. Does that make sense? Okay. This is the last question here. I'm going to erase this. This is the last question for today. So just move this. So before we do this last question, because it's a hefty amount of like derivation, a little bit, we can take a quick break, again, 5 minutes. So then we're just fresh when we're doing that question again. Let's see, we got questions in the chat. If we have sources with different omegas, can't we just use superposition theorem to solve it?
I thought it was the same stuff.
Superposition is
It's like you ignore like one independent source and you just take out the other one. So basically you have only one omega for one circuit. Then you do the other one with the other omega. And for the total stuff, it's just gonna be the sum of the two sub-circuit also. And I have a vague memory of my teacher class.
What is the question I don't?
If you have different omegas, can't you use superposition to solve it? I'm just thinking because your impedances are J omega L, right?
Yeah.
For example,
So it's gonna be different.
it's going to be different for each case.
So for each case, but then once you're gonna do your full circuit, you're
Yeah.
gonna add them up. Because superposition theorem.
Mm,
Because, well, I have a vague memory of my teacher doing that with like one source, which has 2 omega.
okay. It could be done. I think it could be done.
Yeah.
I think it could be done. You just have to be very, very careful about it.
Also super long, but
Yeah, but I doubt that this is like within the scope of this class, you know?
I just have a vague memory of like my teacher showing that in class. That might be why also like why we had it like in the midterm.
Mhm.
So, I just check the notes. I'm not sure about that. Is that chapter 5?
What? Which I don't know. You're taking the class in French, right?
I did.
Who's your professor? Yeah, Goob.
Yeah,
Uh,
he's a pretty good teacher.
mhm.
There's a lot of examples. He's a bit crazy though.
Yeah, this class is like an example-based class. Yeah. Electronics 1, however, especially with Professor Mohammed Ahmed, he does not do a lot of examples. He's not that type.
It's more like church
Yeah.
stuff,
And one thing is like all the proofs that he does,
right?
he's part of the course, so you could expect them on the midterms. So yeah, he always does. Yeah, but he's not the type to ask you about that. He would.
They're good resources outside of the class.
Electronics 1?
Yeah.
There are a couple of resources to learn for Electronics 1 outside of the class, or Electronics 2, not really. Yeah. What happens is that a lot of people come to the Electronics Cookies and Cram. This is where a lot of the learning happens. Yeah. This honestly, we've been getting a lot of feedback this year because the mentors this year are very, very solid. They have good understanding. Yeah, I mean, I'm the one who took it. It started last winter, but I'm talking about other classes as well, like Compark 1, Computer Architecture 1, the math classes as well. Yeah, Jad he's
Full, there's no more room.
yeah, I know. He's one of my best friends. Yeah, Jad. He's the vice chair of IEEE. Yes, he's very, very talented, very gifted, very hardworking. So like people like those, and he's making sure because he's the vice chair, right? And he's making sure that the mentors teaching these sessions are very competent in actually giving out information, making people pass. Because the whole point of this sessions is like as soon as you get to the upper year classes, right? It's hard to pass. So they can get a quick pass like that. So yeah.
Oh yeah, you can apply superposition.
Superposition, yeah.
Yeah. Sur un régime permanent.
Okay.
Yeah.
Okay. Parfait.
Just want to see the example because there is the one specifically.
Mm-hmm.
I mean, it's gonna be fed into some AI.
Also, it's like after this session right now, there's another Cookies and Cram going on starting at, I think it starts at 5 for signals and systems, which is a third year class you guys are gonna have to take. But this one as well is being taught of one of my best buddies as well. So like all the classes we're really stacking up good people to teach them. Because especially in the 5 years, the 5 past years, I don't think we've had anyone teach electronics for Cookies and Cram. It's been dead. Ever since Mohammed Ahmed, that's his nickname. But ever since Momo took over to teach these classes, it's been dead. No one ever really taught it. Yeah. There was no one. I think this year as well, I think it's the first electronics 2 Cookies and Cram ever probably that ever happened. Okay. We're gonna go through this last one right now. Okay. This is a question where it requires a little bit of mathematical skills, and then it requires a little bit of thinking, and it requires a little bit of good understanding from the last module, because this is maximum power transfer in applied and from the last module. So if you look over here, you have this circuit, you know, we got impedances here, and then we have a capacitor in parallel with that resistor here. What it's saying is like a capacitor has been added to maximize the power absorbed by the 4,000 ohm resistor. What value of capacitance should be used to accomplish that objective? So we're trying to find C. That's the part we're trying to find C. And to be honest, I started this question yesterday, but I went to bed. So starting this morning, I woke up late, so I didn't finish it yet. So I'll try to do it right now, and then let's hope that I can get the correct answer that's in the solutions. Because the solutions, I looked at them, it's not explicit. I looked at it, I was like, what is he trying to do? It wasn't making any sense. So let's cook it up right now. For this one, not really. I don't think we got to do that here. Okay. Here's what we got to do though. Okay. So, do you guys remember for maximum power transfer, you need one condition. You need that Z load is equal to Z Thevenin conjugate. Yeah? So, one second here. I had a couple of things I wrote. I started it somewhere. I'm just going to leave it here. So I'm just going to take these ones because I don't want to write it again. Ooh. And then the rest now this one I'll leave it too. And the rest I'll delete. Okay. So this is basically the condition right here, right? So we have ZL equals ZT conjugate. And ZT conjugate is basically RL plus XL, where RL equal to RT and XL is equal to minus XT. Okay. And then this is for real maximum power transfer if you know what VOC is. So we have this circuit right here. If you remember the circuit from class that Professor Gad covered, what happens is that you have here a ZL. That's your ZL. And over here, that's going to be your ZT. The reason I'm doing this is because I want to make it look similar to the slides that he has in class. ZL in series with that ZT. Okay? So now I need to calculate what ZL is. ZL would be equal to 800 plus J. Omega in this case is 5,000. Omega 0.32. So that's equal to 800 J, I think 1600. Yeah, 1600. Now I need to find out what ZT is. Now, just so I don't have to deal with a lot of numbers, I'm going to equate that to R. And then I have C. Now, what's the combination that's going on in here? What type of combination? Parallel, right? So this C, I can write it as XC, which is 1 over J omega C, or minus J over omega C, right? So we're just going to do that. So XC is basically R parallel with 1 over J omega C, which is R times 1 over J omega C over R plus 1 over J omega C. Is this clear how I got this? I just multiply on top and add it on the bottom, just like I do any parallel combination. Okay, now I'm just going to take this denominator and distribute it right here, right? I just want to bring everything to the same denominator. So I have R over J omega C. And then here, it's R times J omega C plus 1 over J omega C. Is it clear with that? From this to this? Okay. Now I'm just going to have R over J omega C times, oh, I don't have room. I'm just going to add a new page. So this is not XC, this is ZT. So ZT is R over J omega C times J omega C over 1 plus R J. I'm just going to write it as J first. Omega C, J, R omega C. This is a plus. Is that clear? I just took the first one and then I flipped the bottom one because it's a fraction. So I multiply by a reciprocal. So this is going to happen. This is going to cancel. So I have something that 1 R plus J R omega C. Now, all I want to do, my goal with this part right now is to write the impedance into something plus J something. That's all I'm trying to do. Because if I have it in complex form like that, it's very easy to identify stuff. So to achieve that, I need to multiply by the complex, it's called rationalizing the denominator. So I'm just going to multiply it by J, 1 minus J R omega C, and 1 plus J omega R omega C. Is that clear? Okay. So now it becomes R times 1 minus J R omega C over 1 minus J R omega C plus J R omega C minus J squared R squared omega squared and C squared. Right? These two are going to cancel. So it's R 1 minus J R omega C over 1 minus J squared is negative 1 R squared omega squared C squared. Okay, minus minus becomes plus. So I have R, I just bring the R inside right here. So R minus J R squared omega C over 1 plus R squared omega squared C squared. Oof, so far so good. Now I have two terms on top, added up together, and I have one big denominator. So I can distribute that denominator between the two top parts, right? I can call this 1 over 1 plus R squared omega squared C squared minus J times R squared omega C over R squared omega squared C squared plus 1. Is that clear? So now I have two parts. I have some value here, and then if I bring this negative inside, plus negative this. And then I have another, let me just write it better here. Minus R omega squared C, 1 plus R squared omega squared C squared. And then this is my second part. So this is ZT. Now we're trying to find Z. ZL has to be equal to ZT conjugate, right? So ZT is equal to this thing, right? So ZT conjugate will be R over 1 plus R squared omega squared C squared, and then plus J will become minus J because complex conjugate R omega squared C over 1 plus R squared omega squared C squared. So these two minus signs will cancel out, and I'm just left with 1 over 1. I'm just left with this. Okay. Now this has to be equal to ZL because that's the condition for it to work, right? Is this condition. If that condition is met, then you have maximum power transfer. And you know you already have maximum power transfer. Why? Because it says that in the question, right? Maximum power is absorbed by the 4,000 ohm resistor. So this has to be equal to ZL. And over here, I said that the ZL equal to this value. Okay. So whatever I got going on here has to be equal to 800 plus J 1600. But now it's a complex number. So that means these two have to be equal. And then these two have to be equal. Does that make sense? So I can write it as R over 1 plus R squared omega squared C squared has to be equal to 800 and R omega squared C over 1 plus R squared omega squared C squared. This has to be equal to 1600. So now I got two equations, and then you know R, you know omega, so one unknown. So I can just do this. R equals 800 times 1 plus R squared omega squared C squared. I'm just hoping I get the right answer here because honestly, I haven't done this beforehand. Or hold on one sec. I think I know what the trick is here. Wait, no, it's not a trick. Never mind. Okay. So I'll just 800 plus 800 R squared omega squared C squared. So I bring all the R's to one side. I bring the 800 to the other side. R minus 800 equals 800 R squared omega squared C squared. So C squared is R minus 800 over 800 R squared omega squared. Is that clear so far? So then C, now I know when you take the square root, you have a plus or minus, but capacitance value cannot be negative. So it's going to be the positive R minus 800 over 800 R squared omega squared. Now, for the love of God, please be correct. If it's not, I probably made a numerical mistake, but this is the step-by-step process to go through it. R is 4,000. So we have 4,000 minus 800. I'm already happy. Why am I happy? Because the numerator is not negative. So because if that would be the case, I'd be freaking out right now. 800. R squared is 4,000 squared, and omega squared is 5,000 squared. 5,000 squared, all under the square root. So let me chunk those numbers in. I mean, it's a capacitor. Got it. We got it. Ah, yeah, we got it. 0.0000001 farad, or 1 times 10 to the negative 6 farad, or is that it? 1, 2, 3, 4, 5, 6, or 0.1 millifarad. So, is it clear on how I got this? Yeah, microfarad. Yeah, I'm already tripping. Hold on, microfarad. There we go. It's 7. It's 7.
Oh, it's 7.
Yeah. Look, 1, 2, 3, 4, 5, 6.
1 times 10 power negative 6.
Oh, yeah, my bad. Yeah, my coffee's over. There we go. Well, we got the right answer though. We got the right answer. But honestly, the process here is this is the hard part. This is the hard part. And that's why when I looked at the solution, it was done in 2 lines. I was like, yo, there's something up, you know? It's like he's trying to gatekeep the knowledge, right? He's trying to gatekeep the knowledge here. So it's like, yeah, okay, let me give the knowledge here. Because I was looking at this yesterday, I was like, had to make me think. But the whole point is, if you have a circuit like that, make it look like in class, and then from there, use the conditions that give you what you want, and then do analysis from there, right? Try to do the math to get into some terms that you know. For example, I know I had ZT, which is parallel, so I just expanded the parallel combination. That's all I did. I expanded the combination, and I wrote it in terms of something plus comp plus J something, right? Why did I do this? Is because I already know that it has to be equal, right? It has to be equal. And I have this in terms of something plus J something. So if I have 2 things that are equal, I can equate the real part, I can equate the imaginary parts, and then from there I can find the values of C. So with that being said, oh yeah, this is the solution he posted, right? Okay, but with that being said, this is I think this is the end of the session, which is stuff that I had to cover. If there are specific questions, I can take them. These notes, I'm not gonna send them to you personally, but I will ask that you go on the IEEE uOttawa Discord server. I will send these notes to the VP Academic, and he will post them on there. So that's one way you can get access to them. All right. So everything that I've done today will be posted on there. The recording. What's up? Whenever the VP Academic decides to, I will send it to him. But he's got exams going on as well. Hopefully by tonight, though. Tonight. Okay. On YouTube, I don't know how long it will take to upload, but we'll try to get it done as soon as possible. I think the recording is still going on strong here. Let me see. Yeah, I think it's going on strong here. Recording is going on strong. So you have access to that. And a couple more things before I end it off is, again, I have intentions of leading more of these sessions in the winter for ELG classes. So I think I'll be taking it for Electronics 1. It was a huge success last year. And then this fall, actually, I had like 38. There's this circuit theory, and just understand one thing here. That's how hard Electronics 2 is. This circuit theory, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 attendance. 10 people showed up, and then we got like 9 people on Zoom. So that's 19, right? And that's CEG, ELG combined. Electronics 2 is only electrical engineers that take that, right? The attendance was 38 total. more than the attendance of the professor. So I'm just that's honestly that's how it was. But yeah, but it was a huge success this year as well. It went very well. It was a huge success. So there we go. So what I recommend is follow IEEE on uOttawa. Get into the Discord server. These sessions going to keep on coming. I'm trying my best to make them as lively as possible, as helpful as possible. So I want to do those. And other classes that I might not teach, good people, solid people are teaching it. I promise you guys. Like people like Jad are teaching it. Signal Systems Josue is teaching it. So there's that. And I'm also the ELG commissioner here on campus. So I have office hours that's posted on the Discord server. So if you ever need help with any like ELG classes, or you want to talk about future ELG classes or whatever it is you want to plan ahead, you guys can always drop by, say hi, talk about anything like that. And I'm always happy to help out. One more thing before I leave, because I know everyone's tired, is in the winter, I am planning an ELG study night where, you're just going to come in as an ELG community and then just have snacks and then maybe energy drinks, whatever it is. I don't have that plan, but we're going to book a room and then we're just going to study for like 3 hours together as a whole. So if you guys are interested in that, please watch out on the IEEE channel. So that's it. Any questions about the thing here? I hope it was helpful. I try my best to cover as much as I can in the 3 hours that we got. All right. I appreciate you all for showing up. Thank you, man. All right. Any questions here on Teams before I finish it off? The chapter notes you mentioned in the beginning. Oh yes, I will post them on the Discord. Now, me personally, I will send them to the VP Academic and he will post them. And all the recording here, I think it will be posted on a YouTube channel that everything works according to plan. All right, no problem. So I'll give it like 2 minutes here on the Teams. You guys are good to leave. But if you have any questions, I'm here for 2 minutes for you to answer. If we need more time, I can go over them as well. Oh yeah, for sure. Take pictures if you want to. Take pictures if you want to.
Sorry, in Discord, in Discord, I didn't understand.
What's up?
You want to put on Discord like this meeting?
Yeah, it's not me posting it.